This is the Cantor set, an uncountably infinite set with a measure or length of 0. It is the simplest example of a fractal, and from a topological perspective is considered a perfect set. Due to its simple construction, yet rich structure, it is a textbook example that illustrates some of the core ideas in both topology and analysis. Moreover, by generalizing its construction, you can produce similar-looking fractal-like sets that have measures anywhere between 0 and 1. In this video, we'll go over how the Cantor set is constructed. We'll then calculate its cardinality and learn why it leads to the possibility of uncountable sets having any length whatsoever. By the end of this video, you will also understand what it means for the Cantor set to be a compact, totally disconnected, perfect set. We start with the points 0 and 1, and all the points in between. We'll call this interval C1. Next, we divide C1 into 3 equal parts and remove the middle third. We are left with these two segments, which we'll call C2. We then do the same thing to each of these. Divide them into 3 and remove the middle third. By repeating this process infinitely, there are certain points that will never get removed. The points left over make up the Cantor set. So it's defined to be the intersection of all these sets from n equals 1 to infinity. But just how large is the Cantor set? How many points really don't get removed? There's a very nice way to calculate this by considering what's called the ternary expansion, or expansion in base 3. The other expansions you're probably already familiar with are the decimal expansion and the binary expansion, which involve representing numbers in base 10 or base 2. The ternary expansion is very similar to binary, but instead of just using the digits 0 and 1, we use 0, 1, and 2. So the ternary expansion of various numbers will all have this form. Now, how do we represent elements of the Cantor set in this way? Let's go back to the original steps we took. After removing the first middle third, we are left with the intervals 0 to 1/3 and 2/3 to 1. Any number left in this left interval will be of the form 0.0 followed by a combination of 0s, 1s, and 2s. And any number in the right interval will begin with 0.2, again followed by 0s, 1s, and 2s. The numbers which we've removed from the middle will begin with 0.1. So at this step, we've removed all the numbers that begin in this way. Now let's take a look at the next step. The left half are all numbers that begin with 0.0. So by removing the middle third of these, we are left only with numbers that begin with 0.00 and 0.02. All these numbers with 1 in the second digit have been removed. Similarly, if we consider the right half, we are left with the numbers that began with 0.20 and 0.22. And of course, we continue this process indefinitely. At each nth step, we simply remove numbers that have a 1 in their ternary expansion in the n-1th digit. So after an infinite number of steps, we will have removed all numbers that contain a 1. And as a result, the Cantor set will simply be the set of all numbers in the unit interval that consist of any combination of only 0s and 2s in its ternary expansion. Or to be more precise, a number for which at least one of its ternary expansions contains no 1s. So how big is this set? Well, it must be uncountable. And here's why. Every number in the Cantor set will be of this form. By simply dividing every number in the set by 2, we get a 1-to-1 correspondence between the Cantor set and the set of numbers written in their binary expansion. But every number in the unit interval can be written as a binary number. So since the unit interval is uncountable, both of these sets must be as well. Now that we know the Cantor set is uncountable, let's consider its length. How in the world do we go about counting the length of this set? There are several ways to do this, but my favorite is the following. At the first step, we have just one line segment with a length of 1. At the second step, we have 2 line segments each with a length of 1/3. So the total is 2/3. At the third step, there are 4 line segments each with a length of 1/9. In general, at each step, we will have a pattern where there are 2 to the n-1 pieces, each with a length of 1/3 to the n-1, giving the total length at each step equal to these numbers multiplied together. To find the length of the Cantor set, we just need to take the limit as n goes to infinity. And since 2/3 is less than 1, this must go to 0. So although the Cantor set is uncountably infinite, its length is 0. I find this result truly fascinating. This means that by just rearranging an uncountable set, you can obtain a set of any arbitrary length. The entire real numbers is infinite in length. But since it's uncountable and any interval you pick is uncountable as well, there will always be a one-to-one correspondence between them. But the Cantor set is also uncountable. So not only will there be a one-to-one correspondence between sets of any positive length, but there's even a one-to-one correspondence with the Cantor set of length 0. This is in stark contrast to sets that are countably infinite, which if you saw my previous video on measuring the rationals, you know that no matter how you rearrange these, they will always have a length of 0. Let's now consider the topology of the Cantor set. The most basic topological question to ask is whether it is a closed or open subset of the unit interval. Well, we began with the closed interval between 0 and 1. At each step, we construct more and more closed intervals. The Cantor set, being the intersection of all of these closed sets, must therefore be closed as well. Next, the Cantor set is compact. This means that every open cover of the set has a finite subcover. And thanks to the Heine-Borel theorem, this is equivalent to a set being closed and bounded, which the Cantor set, since it's a subset of the unit interval, necessarily is. The Cantor set is also totally disconnected. This means that there's no subinterval anywhere. Every single point in the set is not connected to any other point in the set. The entire Cantor set is composed of singletons and seemingly exists as a kind of uncountably infinite dust. Additionally, the fact that it is closed and totally disconnected implies another property, namely that it is nowhere dense. This means that the interior of its closure is empty. Or in other words, if you take the entire Cantor set plus all its limit points, then this whole set also contains no open intervals. A nice counterexample to this is the set of rationals in the unit interval. They contain no subintervals and form a totally disconnected subset of the reals. However, they are neither open nor closed, and their closure is the entire real line. So the new set of the rationals plus all their limit points do contain intervals. And in this case, the rationals are not nowhere dense, but instead are dense in the reals. The key here is that the Cantor set is a closed set, while the rationals are not closed. Now, I mentioned at the beginning of the video that the Cantor set was a perfect set. What could this mean? In the subject of topology, a perfect set is a set which is closed with the added criteria that every single point in it is a limit point of the set. So the Cantor set being perfect means that it consists only of limit points. And there's a very nice short way to prove this. We already know that C is closed. Let's start by taking an arbitrary point x in C. Then we'll consider any open interval around x. We'll call it I. Now remember, since the Cantor set is nowhere dense, this interval is a subset of R, not C. Additionally, since x is in C, then by definition, it's in the intersection of all the CNs going from n equals 1 to infinity. So at some point, we will be able to find one of these CNs such that it is entirely contained in I. But once this occurs, then we have found at least two other points in the Cantor set that are also in I, namely the endpoints, since they will never be removed. In fact, if you continued with the iterative process, you will find a countably infinite number of endpoints that belong to the Cantor set and also lie in the interval I. But this is exactly the definition of a limit point. No matter how small I is, we can always find at least one other point in the Cantor set inside of it. And since this process works for any arbitrary point x, this means that all the points in the Cantor set are limit points. So the Cantor set really is perfect, in the best kind of way.